Welcome to Online Algebra 2. Today, we'll cover section 1-2, the properties of real numbers. So our objective here is to graph and order real numbers, to identify properties of real numbers. And what you should know, the essential understanding is that the set of real numbers has several special subsets that are all related to each other in particular ways. And you probably heard of most of these before. In fact, this is a pretty standard thing to go over in the start of a math class here, especially algebra. So algebra involves operations on and relations among numbers, including real numbers. And also in chapter 4, we're going to talk about something called imaginary numbers, right? But that's not it yet. So rational numbers and irrational numbers form the set of real numbers. And we can graph all these things as a point on the number line. So even if you have a nice number like 4, right, that's clearly right there on the number line. Radical 5 is a little bit harder to figure out, but we can use a calculator to sort of estimate where on the number line it would go. 0 is nice and easy. Negative 1.5, you can sort of eyeball that, and it's halfway between -2 and -1. But the point is that all these things are real numbers, so we can actually graph them on a real number line. Okay, so let's go through all the different subsets of the real numbers. Okay, so these are all real numbers, and they are anything that could be graphed on a real number line. Okay, so real numbers. Okay, all of these different subsets of numbers kind of have abbreviations, and we typically use uppercase letters to abbreviate sets. And for the real numbers, we're going to use a special one. We're going to use an R with 2 little sticks on it. Okay, but the capital letter R is the abbreviation for real numbers, but we do like to put these 2 little sticks on that too. Okay, so let's start with the most basic, natural numbers. Natural numbers are the numbers that we use to count. So it is 1, 2, 3, 4. And notice that this is way inside of all of these. So this is the most specific set. Okay, this is the most limiting. Okay, so it's 1, 2, 3. These dot 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 dot. The ellipses mean that it keeps going on forever in only one direction. So next would be 4, then 5, then 6, then 7. And for natural numbers, we are going to use the abbreviation of N. Okay. Whole numbers. Whole numbers and natural numbers are the same thing almost, except for 0. Okay. 0 is a whole number. It is not a natural number, right? When you count something, you don't start with, oh, that's 0, then 1. No, right? You start with, hey, that's the first thing, then the second thing. Whole numbers includes 0 in the set, and its abbreviation is a capital W. Integers are the natural numbers, 1, 2, 3, and their opposites, -1, -2, -3. Okay, so, and 0. Integers are no fractions, no decimals. So none of these sets include fractions or decimals. And you can see we're getting a little bit bigger. We're getting a little bit more numbers each set. So the natural numbers, just 1, 2, 3, 4, 5, 6, 7. Whole numbers, 0, 1, 2, 3, 4, 5, 6, 7. Integers, now we have all those numbers and the negative numbers. Now, you would think that the abbreviation for integers would be a capital I. But if you look, there's 2 things with an I. So they can't both be I. And in fact, the set of irrational numbers would be I. So that means that we need something else for integers. And we're going to name it Z. Why Z? It looks good. Then we have all the fractions, all the decimals, all positive numbers, all negative numbers. So we have all these different types of decimals. Okay, we'll talk a little bit in a second about what's the difference between these two. Rational numbers, the abbreviation for rational numbers is a Q. All right, so let's look real quick about the difference here between rational numbers and irrational numbers. So the definition of a rational number are all the numbers you can write as a quotient of integers, something over something else, as long as the denominator is not zero. Okay? These include decimals that stop, decimals that repeat. So 6.1 is a rational number because it's a decimal that stops. 5 over 4 is a rational number because you can write it as a fraction. 2 is a rational number because you can write it as a fraction. So any of these, you can see that the natural numbers, the whole numbers, and the integers are all inside of this set as well. So rational numbers covers all of these, right? We always name things with the most specific one, but 3 is a rational number. It's also a whole number. It's also an integer, but it is all those things, okay? Because it's the most, it's the one that's all the way inside there. 0.22222 is a rational number because it's a decimal. Well, it kind of stops, but if we wrote it like this, if we wrote it like 0.2 repeating, then that's a rational number because it's repeats. Irrational numbers have decimal representations that neither terminate or repeat, okay? And they cannot be written as quotients of integers. So the irrational numbers are pretty much going to be weird symbols like pi. In a later chapter, we'll talk about another one called e. But these represent numbers that don't stop. And the most typical way we get a number that never stops is if you have a square root of something that is not a perfect square. Those never stop. Okay? So what we want to do when we're trying to figure out the subset of real numbers that something belongs to is we classify the variable by naming the subset that gives you the most information about the number. Okay, so what is the most specific? Okay, so if you were going to write the number 3, I would classify that as a natural number. If you were going to write -3, you would classify that as an integer because that is the most specific. Yes, it is a rational number as well, but integer is more specific, right? If you have -3 over 2, the only thing that we can classify that is irrational. Yes, it's real, right? All of these are real. Everything that we're talking about now is a real number, but we don't just say that, oh, hey, that's a real number. No, I want to be as specific as possible when we are trying to name the subset that that number belongs to. Let's try it with a little word problem here. And your school is sponsoring a charity race. What set of numbers does not contain the number of people who participate in the race? Well, let's think about this for a second. Could a natural number be the number of people that are in the race? Yeah. What are natural numbers? 1, 2, 3, 4, 5, 6, 7, right? Those represent the number of people in a race. Yeah, it could work. Integers could work as long as you don't have any negatives, right? Because integers include numbers without fractions and decimals that are positive. Rationals include numbers without fraction or decimals that are positive, right? Because you can't have half a person running in the race. But the only one that does not contain the number of people is irrational. You cannot have an irrational number of people run in a race. If each participant in the race made a donation of $15.50 to a local charity, which subset of real numbers best describes the amount of money raised? Well, for that, I would say it had to be rational as well, right? Because this is a decimal, right? Or if I want to use the abbreviation, which is a Q, that's a decimal. So if 2 people ran into the race, it would be a integer or a natural number, right? That's more specific. But if 3 people ran into the race, then we're going to have some sort of decimal here. And the decimal does stop. I think I have one more maybe. Okay. List all the numbers from the given set that are members of the real number subset of rationals. So I'm looking for rationals. So that means which one of these is rationals? 14 is rational. The square root of 6 is not rational because it's a radical that doesn't stop. Negative 19 is, 0 is, 5 over 6 is. The square root of 16 is rational. It is rational because it's 4. This is a decimal that repeats. This is a decimal that stops. So the only thing in here that is not rational is the square root of 6. So all those numbers right there are rational numbers. All right, so let's look at a number line. Okay. So when we graph numbers on a number line, and this might seem a little basic, but we just have to make sure we're putting them in the right spot. And the easiest way to do this is to change them into a decimal. So negative 5 over 2 is pretty easy to spot on here. It is negative 2.5. So we're going to just change that to its decimal form, and I can put that pretty easily halfway between 2 and 3. Now the square root of 2, you might not know off the top of your head, is 1.4. So that's going to be, so 1.41. So when we put that, it's not quite halfway, so maybe like right there. And 2.6, that's easier to graph a little bit past halfway on that point. So this would be negative 2.5, 1.4, and 2.66, and repeating. So number line, very simple. Just put your numbers on the right spot on the number line. The number line is helpful for ordering several numbers. For two numbers, however, it's easier to show order or compare these using the inequality symbols of greater than or less than, or of course greater than or equal to, less than or equal to. So these are inequality symbols. And again, when you're comparing two numbers, compare the same thing. So if we're going to compare the square root of 17 to 3.8, it's much easier to change the square root of 17 to a decimal. And even if I didn't have a calculator, I could do this because I know that the square root of 16 is 4. So this is going to be a little bit bigger than 4. In fact, it's 4.123. Okay, so if I'm going to compare that to 3.8, 4.123 is greater than 3.8. And again, the easiest way to do this is to change everything to a decimal, either with a calculator or with some logic. And how do the square root of 26? Let's do this without a calculator. Well, I know the square root of 25 is 5, and I know the square root of 36 is 6. So this is going to be less than, because square root of 26 is going to be less than the square root of 36, which is 6, so it's going to be less than 6.25. Let a, b, and c be real numbers such that a is less than b and b is less than c. How do a and c compare? Well, this is a property that we'll talk about later, but if you think about it, let's just plug some numbers in. A is less than b, so that's 1, and b is 2. And so 2 and c, let's make c 3. Now we're comparing these two. When I compare 1 and 3, obviously 1 is less than 3. So this is something called the transitive property, and we can say that a is less than c. So you can say that if a is less than one thing, and that new thing is less than this third thing, the first thing is going to be less than the third thing. Okay? So hopefully that made a little bit of sense. Okay, so our next essential understanding is that the properties of real numbers are relationships that are true for all real numbers, except for some special things like 0. One property of real numbers includes a single number 0, and it is the additive identity for real numbers. and 0 is the one real number that has no inverse. It has no multiplicative inverse. Okay, so there's these two special types of numbers in our mathematical system, right? They're um, inverses and identities. Okay, so first, when we talk about inverses, right, if we're talking about multiplication and addition, right, our two main operations that we use in our number system, the additive inverses are opposites. Okay, so if we have a, the inverse is negative a, and whatever the number it is, its additive inverse is always the number that adds to 0, my identity. Okay, so here's the two important things: inverses and identities. Inverses are the thing that you can add or multiply with to give you the identity. The additive identity is 0 because when you add 0 to something, nothing happens. The multiplicative identity is 1 because when you multiply 1 to something, nothing happens. Okay? And the way that we get the multiplicative inverse, the thing that I can multiply any number by and get the identity, is the reciprocal. Okay? So the way I get a reciprocal is I just take a fraction and I flip it over. So the multiplicative, and that's called the multiplicative inverse. So the multiplicative of any non-zero number, a, is 1 over a. So again, 8, the inverse would be 1 over 8. Negative 5, the inverse would be 1 over 5. 2 over 3, the inverse would be 3 over 2, right? We just flip the fraction around. Top becomes bottom becomes the top. So what we're trying to understand here is that addition has some special properties, multiplication has some special properties, and we can look at a few of these properties and see a little bit how they work. Okay, so these are the properties of all real numbers. And again, we have two columns here, addition and multiplication. Okay, those are our two main operations in our mathematical system. You're probably thinking about, what about subtraction and division? Subtraction is just addition with negative numbers. Division is just multiplication with fractions. Okay, so all these properties hold for subtraction and division if you use them the right way. Okay, so first, closure. Closure is very simple. If you have a real number, if a plus b is a real number, if a is a real number and b is a real number, when you add them together, you get a real number. Okay, you multiply them together, you get a real number. So if you have two real numbers, there's no way to get something that is not real. You can get things that are irrational, or you could get things that are integers, or you can get any of the other types of real numbers, but you're going to get a real number. Commutative property. Sure, you've seen this one before. A plus b is equal to b plus a. I can add things in any order I want or multiply things in any order you want. Now, the commutative property works for addition. It also works for subtraction, provided that you keep the signs of everything the same. I'm sure you've seen this example before. You're going to say, well, wait, a plus b is not the same thing as b, a minus b is not the same thing as b minus a. That is true. That is not the same, because in this first part, the b is negative, and in this second part, the a is negative. If I wanted to write this expression the correct way, I must keep the b negative. And now these two show the commutative property and how it would work for subtraction. And for division as well, right? It would look weird with this. Those are not the same, obviously, okay? But what we're trying to say here with division, if we use division as multiplying by a fraction, right? A times 1 over b is going to be the same as 1 over b times a. So as long as the same thing is in the denominator, as long as you're dividing by the same thing, you're going to get these properties to work for addition or subtraction or division. As far as the associative property is concerned, the thing inside the parentheses has to be different. The thing inside the parentheses has to be different, and we're basically just saying there that you can do them in any order that you want. Again, the two special numbers here, 0 is the additive identity because when you add 0 to something, you go back to where you started. 1 is the multiplicative identity because when you multiply something by 1, you go back to where you started. Inverses for addition are opposites. Inverses for multiplication are reciprocals. And our last property, the distributive property, in this case it's multiplication over addition, right? We just take this a and we multiply it to both of those two to give me my expression. All right, so let's see if we can look at something and say what property it represents. Okay, I have two things. They're multiplying together. They're giving me 1. This is an inverse. And because it's multiplication, property of multiplication, inverse property of multiplication. Okay. Next one. 3 times 4 times 5 equals 4 times 3 times 5. Now, many times I've seen people make this mistake by just looking at this problem. It says, oh, it has parentheses. That's the associative property. It is not the associative property because if you look at the associative property, the thing inside the parentheses has to be different. That's not what's going on here. The thing inside the parentheses is the same as 3 times 4. It's just different order. So this is the commutative property. Okay, commutative property. Okay. This property turns into this. That is the distributive property. Okay. And use properties of real numbers to show that this expression is equal to 3. Okay, well, I don't have to do these in this order. I could change it to negative a plus 3. And then I could use the associative property to say that a minus plus a negative a, and then do the 3 on the outside. And then this is two opposites, so it turns into 0, and that gives me a 3 each time. Okay? And again, you wouldn't go through this whole thing because these are all, there's no multiplication here. You can just drop these parentheses. Just make sure you have the negative in front of the a, and the a and the negative a are opposites and will cancel each other out. Okay, so you can look through some of these lesson check problems to see if there's any that you wouldn't understand. You can think for yourself, something that represents whole numbers, maybe counting things, or think about an example from your daily life that would use each one of those types of numbers. Quick properties. This is the additive inverse, and this is the associative property. Notice that what's inside the parentheses has now changed. Another name for a reciprocal is a multiplicative inverse, and that is the actual correct name. And then you could look through the rest of these. Okay, that was 1-2 properties of real numbers.